a square into okay, can we divide a square into triangles having equal area? So here, of course, the answer is yes, as you can, many of you can give me some divisions. So let me also draw some of them. So we could, for example, divide. One obvious way is I can just divide in half, but let me, is there some other way we can do this? So I could divide into two pieces, and now each of them I divide into four triangles and two triangles. Okay, this is one way. And instead of two, I can let's say I take one third distance. Okay. And again, I divide each of them into two parts. So you see, if we follow this pattern, we can get any even number, right? Any even number of triangles. But let us just see if we can get some other patterns, okay, just for curiosity. So we could also have done something like this. I divide this diagonal into three equal parts. Okay. Then can you see that all these triangles, these three triangles, you see their bases are having the same length and their height is equal. All of them have the same height. Okay, so they all have the same area. Same way I could divide this side. Okay, so if I uh, divide the diagonal into n equal parts, I will get 2n. I will get 2n triangles. Okay, and not only this, you could even mix up some. So dividing into triangles, the word used is triangulation. Okay, so let's say I want to divide into, this is one third. Okay, so then this area is twice this area. So if I divide this like this, now all three have the same area. And now I can just make triangles and they will have to have the same area, right? So you could divide in various ways, but what you notice is we are always getting an even number of triangles. So um, so mathematicians, they, I don't know. Yeah, so you would not have thought that somebody would wonder about this, like, will we always get an even number of triangles? So some mathematician actually thought of that, and it was given in the American Math Monthly in 65. I forget the name. And then Paul Monsky, after 5 years, he said that. So he says that whenever we whenever I divide a square into triangles having equal area, then we will always get an even number of triangles. Okay, so this is the theorem which we will look at today, that why this should happen. So this is the Monskys theorem, and so let us make a first simplification, that if I can divide some square into triangles having equal area, and suppose we can get an odd number, so the same should happen for the unit square. Okay, so okay, we'll show this for the unit square, because if I can do it for any square or some square, I can do it for the unit square. Okay. It will be this fact will be used later in the proof. Okay. So so what we will do is suppose we divide the unit square. Okay, unit square means I'm sure you all know, but just to, so here I have the origin, then I have 1 0 and 1 1 and 0. So this is what I mean by unit square. So suppose we divide the unit square into k triangles. Each having the same area A. Okay, so then what will happen? Then the total area of this square is 1, and I have k triangles, so each having area A, so I get this. Okay, so now we want to show that the theorem is saying that k has to be even. Okay, so k will be even, then A will be 1 over of the form 1 over 2L, right? Uh, so where L is some natural number. Okay, so we want to see, okay, how I can say that some rational number is of this type, right? If I can get some way to show that the area will have to be like this, then that k will be even. Okay, this comment will become clear, but basically you see, we want to see whether 2 divides the rational number in what way. Okay, so I will make it clear. So let Okay, I take a non-zero rational number, and so then we can uniquely write, I can write A as some 2 power r into some m prime by n prime, where m prime and n prime are odd, and this is in a unique way. Well, uniquely, okay, so we'll assume that whenever I have some negative rational number, so I'm putting the top part as an integer and the lower one as a natural number. So I don't say minus 3 by 2 is same as, okay, I will not, so if I have minus 3 by 2, I will not write it as 3 by minus 2. Okay? So we'll just keep this. So then it will be unique. Uniquely, I can do this. So what we will do is we define, see, because we are interested in what power of 2 is coming in the rational number. So we define the 2 norm, okay, of A as over power of 2. Okay, that is the, and norm means it is the usual norm. Okay, so the absolute value, some of you may be knowing this, so is called the usual norm. And norm is just a sophisticated word for size. We say the size of the rational number, you look at the absolute value. That is the usual size. Here, this is the 2 norm. Okay, we put this subscript. So we are, you should think of it like we are measuring the size of the rational number, but with respect to 2. Okay, this is some different notion of size. We will see why we want to think of this as a size. We will see that. Okay? And one more thing over here, for 0, we will just define the norm of 0 to be 0 itself, okay? Just like the usual norm. Okay? So let us get used to this notion. So let us look at some rational numbers. What will be norm of, let's say, 17 by 24? Okay, I'll just write down some of them. You think about it. What will be norm of 50 by 11? What will be norm of minus 3 by 2? What will be norm of 27 by 'Okay, let us try to see what we get. Now for 17 by 24, what will I do? So this part, I will call it a odd rational number. Okay, I'm just making that term. So odd rational number means that. So whenever we say rational number, we'll assume there are no common factors. Okay, so for an odd rational number, so both numerator denominator are odd. So what is the odd part of 17 by 24? So we can write 17 by 24 as, so 8 3s are 24, right? So 1 over 8, and I have 17 by 3. Okay, so the odd part is this. So the 2 norm will become 8. Okay? 1 over the power of 2. Okay, you remember. So here, whatever power of 2, so here the power is minus 3. So I get 1 over 2 power minus 3. Okay? So let us look at this one. So here I have 50 by 11. So 50 by 11 I can write as 50 is 25 into 2. So 2 into 25 by 11. So here I will leave it to you. Minus 3 by 2 is just minus half into minus 3. Minus 27 by 11 is just 1 into minus 27 by 11. Okay, so what should be the two norms? So for 50 by 11, the power of 2 is 1. So I will get 1 over 2. For minus 3 by 2, the power of 2 is minus 1. So I will get 2. Okay. So for minus 27 by 11, the power of 2 is 0. Okay, so here I just get 1. Okay, so let us look at some properties of this 2 norm. Okay, so this is the, and now let us see why we want to think of it as a size of a rational number. So first thing you observe is that for negative rational numbers also, so whether it is a or both the rational number and its negative have the same norm. Okay, so first property is whatever rational number I take, the norm of a is always non-negative, and okay, this is one. Okay, let me just, before this, let me just see this norm, 2 norm is giving me a function from rational numbers to what is the codomain. Okay, so the codomain is 1 over 8, 1 by 4, 1 by 2, 1, 2, 4, and so on. Okay, this is the, these are the values, and of course 0 will go to 0. So the non-zero rational numbers, they will take values like this. Again, look at the definition. You see, if any rational number I write like this, so the 2 norm is just some power of 2. So these are the values it takes. Yeah, so clearly the values are all non-negative, and except for it is 0 if and only if the rational number is 0. That's just from our definition. Okay, so this is a property which is similar to the absolute value, the usual norm. Okay, let us see another property. Okay, so another property is that if I take any two real numbers, rational numbers, what will be the 2 norm of the product? So we claim that for an absolute value, it is the product of the norms. We claim it is same for the 2 norm. Okay, so before proving this, let me just make a comment that this is just saying this map is a homomorphism. If you notice, this side is a group under multiplication. This is also a group under multiplication. Okay, it is a cyclic group. And this is just saying it is a homomorphism. Okay, so let us look at a proof of this. So suppose I write A is 2 power R into C, and B is 2 power S into D, where so now C and D are odd. Any rational number I can write like this. So what will happen to AB? So AB will be 2 power R plus S into CD. And because C and D are odd, So their product will also be odd. So from this, what can we say? The 2 norm of AB should be 1 over the power of 2, right? But this is nothing but 1 over 2 power r into 1 over 2 power s, which is the 2 norm of A into the 2 norm of A. Okay, so this proof was quite simple. Okay. So we have proved this property. Now we can also add rational numbers. Let us see what we can say about addition. So what if I write A plus B, then how do I write it? Okay, A is this, B is this. So we'll have to make some assumption. Okay, so let us assume that suppose the 2 norm of A is greater than equal to 2 norm of B. When will this happen? So this is if and only if the 2 norm of A is 1 over 2 power R, 1 over 2 power S. You may wonder why we are taking 1 over 2 power, right? Why couldn't we just take 2 power R? Okay, so that will become clear now once we see what happens for addition. Okay, so when will this happen? This is if and only if 2 power R is, this is if and only if R is less than equal to S. Okay, so when this happens, now what I can do, I can write A plus B as, remember A was this, B is this. So R is less than equal to S. So I can write 2 power R, I can take it common, C plus 2 power S minus R B. Okay. Now this part may be divisible by 2, right? It could have another 2 could divide this. Okay, so I will write this as 2 power R prime into some E where E is odd, and R prime could be greater equal to R. Okay, so then what do we get? That the norm of A plus 2 norm is 1 over 2 power R prime. Okay, I don't know whether this is odd, so 1 over 2 power R prime. But R prime is bigger equal to R, so this is 1 over 2 power R. But 1 over 2 power R was nothing but the norm of A. Okay. So what we have shown that one of them will always be bigger, right? Either norm A is bigger than norm B. So I will not say 2 norm. Okay, I'll just say norm. Or the norm B would be greater equal to norm A. So one of them is bigger. Whichever is bigger, the 2 norm of the sum is equal to or is less than equal to this. Okay, let me just write it down. So if norm A2 is okay. So this is something which is unfamiliar, right? It looks, I mean, for the usual modulus, absolute value, you don't have this. But this is something special about the 2 norm. But you see that from this condition, I can say that uh, the 2 norm of a plus b less than equal to 2 norm of a plus 2 norm of b, right? Because we have seen that the 2 norm is always non-negative. So whatever is the 2 norm of b, I can just add it. It will still keep this inequality. Okay, so again, it is satisfying this property, which is satisfied by the absolute value. Okay, so these are the reasons why you would like to think of the 2 norm, this 2 norm also as a size of a rational number. So this is just a intuitive way of thinking. So don't worry about why, just if the definition should be clear to you. And so this is the definition and these properties. Under multiplication, it is behaving just like, okay, I'll just put a star under multiplication, and under addition, we have this. Just keep these two things in mind. Another fact which we would like is that if the 2 norm of A is strictly bigger than the 2 norm of B, then again, following this equivalence, R should be strictly less than S. So now this S minus R is, okay, it is, let me write it down. So okay, this we have seen. So the 2 norm of, sorry, yes, let me write A plus B will be 2 power R. Okay, that's just what we had here. So now 2 power S minus R into D is even, okay, and C is odd because here 2 divides this, right? S minus R is positive, so 2 divides this, it is even, and C is odd. So now this whole thing is odd. Okay, so in this case, I can say that norm of A plus B will be just 1 over 2 power R, and that is nothing but the norm of A. Okay, so another result what we get is if one of them is strictly bigger than the other one, then the 2 norm of is equal to the bigger one. Okay, whichever one is bigger, A is bigger here, it is equal to A. Okay, these 3 facts we will use very in what will follow, that it is under multiplication, I get this. Under addition, when it's greater equal to, which is where it's the bigger one, I can say it is less than equal to that. But if it is strictly bigger, I can say it is equal to the bigger one. Okay, just keep these facts in your mind. We will use them. And finally, why did we look at this 2 norm? Let us come to that. So we were trying to look at this, right? Monskys theorem. And if we divide the unit square into k triangles, each having area A, then we have this 1 is equal to Ka. Okay, so I'll continue from here. So if 1 is equal to K times A, then if I take the 2 norm on both sides, 2 norm of 1 is 1, I will get 2 norm of k to 2 norm of a. Okay, and I want to show that k is even. So if k is a natural number, then k will be even if and only if, what can I say about the 2 norm of k? If k is even, no, I'm not saying power of 2. K is not a power of 2. K is just even. You can look at these examples. Suppose k is even. Right? If I had, suppose I had, let's say 24, then what is the 2 norm? I get 24 will be 8 into 3. So I'll get again 1 by 8. So look at this. Okay, if a is even, now it's a natural number. So this r has to be greater equal to 1. Right? So 1 over 2 power r will have to be. So if you look at this values, the values will either be half, 1/4, 1/8 for even numbers. Right? Some positive power of 2 will come out. Okay, some positive power comes out. So it will be 1 over some positive power of 2. So I will get only these values. In particular, I can say it's strictly less than 1. Okay, and for an odd number, it will be equal to 1. So this is, so what we have seen is that if k is even, then the 2 norm is strictly less than 1. And if k is odd, then the 2 norm is equal to 1. So that means this is if and only if. Okay, if the 2 norm is not less than 1, then it has to be odd. Okay.